In this video, I'm going to go over a few examples related to friction. So first example, a 3 kilogram dry steel tray is at rest on a dry steel counter in the kitchen. Mr. Omar applies a horizontal force on the steel tray. For each given applied force, determine what the force of friction would be. All right, and on the right-hand side, I wrote out what the coefficients of friction are. So it's 0.78 for the coefficient of static friction and 0.42 for the coefficient of kinetic friction. Those numbers are for dry steel sliding against dry steel. So first of all, A, 10 newtons. So if Mr. Omar pushes with an applied force of 10 newtons, what will the force of friction be? So just to kind of show you with the free body diagram what's going on, this is the tray, and the tray has a force of gravity on it, downwards. It has a normal force from the tabletop upwards on it. These two are equal in size because the tray is not going to accelerate up or down off the counter or into the counter. Now Mr. Omar is going to apply a force on it in the forwards direction, that's horizontal, and the force of friction is going to resist that force. Now the question is, what is the force of friction? Okay, if the applied force is 10 newtons, what is the force of friction? Is it the same size as the applied force? Maybe, maybe not. Okay, so what we have to calculate to start with is what I call the maximum static friction. So static friction, if you recall from the previous video, can take on a whole range of values from 0 newtons all the way up to some kind of a maximum value. And the way to calculate it is with the formula for friction. So the formula for friction was introduced last video. I'm writing it out here. Force of friction equals mu times the force of normal. Now for the subscript for the coefficient mu, I wrote S, S standing for static. Now when I calculate this out, I'm given the value of the coefficient. As for the normal force, I'd like to point out that in this situation, the normal force is equal in magnitude to the force of gravity. Okay, this is true for a lot of situations when you're on a horizontal surface. A lot of times the normal force just equals the force of gravity. Not everyone though. Okay, we'll do examples where they're different later on. So if I continue on here, the force of gravity has its own formula, which is mg. And now I can calculate this out. So this is 0.78 times the mass, which is 3.0, times the gravitational field strength, which is 9.8. I'm going to put that into a calculator. And that gives me 23 newtons when I round it to two significant figures. Okay, so that's the maximum value that the static friction can take on. So I'll write a little sentence here. Static friction can take on values from 0 to 23 newtons. So that means that when Mr. Omar pushes with 10 newtons, 10 newtons is not bigger than 23. So that means this tray is not going to move, and static friction is going to take on a value of just 10 newtons. Okay, so static friction will just match Mr. Omar's 10 newtons to keep the tray at rest. Now part B, what if Mr. Omar pushed with 20 newtons? Well, 20 newtons is still not bigger than 23 newtons. So it's going to stay at rest. Forces are going to be balanced, and static friction is going to take on a value of 20 newtons to keep it at rest. But what about when we get to 30 newtons? Okay, now 30 newtons is larger than the 23 newtons. That's the maximum static friction. So now it's going to move. Okay, it will actually slide once he applies 30 newtons. And since it slides now, we have to change from static friction to kinetic friction. So now I'm going to calculate out the force of kinetic friction, which will be the same formula for friction, however, using the kinetic coefficient. And basically all I'm changing is the 0.78 changes to 0.42, the kinetic coefficient. That'll be times the normal force, which is equal to the force of gravity, which is equal to mg. That part all stays the same. And now I will calculate this out. So I'll get my calculator out. And that gives me 12 newtons when I round it to two significant figures. All right, so when we overcome the static friction, the object moves, friction turns to kinetic, and the kinetic friction is going to be 12 newtons. Kinetic friction is going to be 12 newtons. And when Mr. Omar raises the force even more to 40 newtons, well, it's still going to be moving. It's still going to be kinetic friction. So it's still going to be 12 newtons. Okay, that's a difference between static and kinetic. The static values can take on a whole range of values. When it's kinetic friction, it can only be one value. And in this case, it's 12 newtons. All right, so there's your first example there. Goes through a lot of concepts, actually, especially emphasizing the difference between static and kinetic friction. And it also shows you how to make use of the formula. All right, question 2. Mary pushes a 12 kilogram box across the floor, and it accelerates at 3 meters per second squared forward. If the coefficient of blank friction between the box and the floor is 0.25, determine Mary's applied force. Now I left a blank there because I want you to think about what word goes in there. What kind of friction are we talking about? Static or kinetic? So since the box is actually moving, it's actually sliding, it is kinetic friction that we are talking about. Give myself a little more space here. Okay, so now I'll try to solve this. I'm going to start with a free body diagram. So this box is going to have, it's 12 kilograms. It's going to have a force of gravity. It's going to have a normal force. And once again, these two are going to be balanced. Okay, this box is sliding horizontally. There is no vertical movement at all, so the vertical vectors should be balanced. Horizontally, we have the applied force, which we were asked to find out what it is. And we're going to have a force of friction. And the force of friction is going to be smaller than the applied force. And I know that it's smaller because I know that it accelerates. Okay, it says it accelerates, so since it accelerates, the forces are not balanced. All right, so I've got to figure out how much the applied force is. First thing I will do is list some stuff out. So I know that the mass is 12 kilograms. And I know that the acceleration is 3.0 meters per second squared forward. And I know that the coefficient of kinetic friction is 0.25. All right, those are the things I know. When you know both mass and acceleration, if you've been doing force problems long enough, you'll realize that it's useful to know both of those. Because when you know both of those, that means you know the net force. Okay, Newton's second law says the net force equals mass times acceleration. So this is a good starting point. My whole right side of the equation, I have the numbers for. Now, in terms of the left side of the equation, the net force, let's think about what the net force is going to be. So we don't have to worry about the vertical forces because they cancel out. So the net force is just going to be the horizontal forces, like what's left over, right? It's what's left over when you take the bigger one, which is the applied force, and take away the smaller one, which is the force of friction. But being careful to make sure you write each of those forces inside of magnitude bars, because we're taking away the sizes of them. Okay, the larger number of newtons minus the smaller number of newtons. And then, so that gets us an equation that we can now isolate for what we're asked for, which is the applied force. And I can isolate that by simply adding the force of friction to both sides. Now I'm going to continue from here. So mass times acceleration, and just copy that down. I'm not worried about that. I know all the numbers for that. However, the force of friction, like what I'm given is the coefficient of friction. So I'm going to replace the force of friction with the formula for the force of friction, which is mu times normal. And just like last time, the normal force happens to be just equal to or balanced with the force of gravity. So I can replace the force of normal with the force of gravity. And the force of gravity is mg. So I can plug in all the values now, though I will do one more step just because it's my preference. I see that both of these terms have an m in it, so I'm going to common factor the m. This is not an essential step. As I said, it's my preference to factor whenever I'm able to factor. All right, now I'll fill in the values. So the mass is 12. And then the acceleration is 3, plus the coefficient, which is 0.25, times 9.8 for g. And that'll give me my answer. I'm going to put that in the calculator. So that gives me 65 newtons. Yeah, 65 newtons to two significant figures. Okay, I'm actually going to add part B to this question. Part B. What if Mary wants to push it at constant velocity? Okay, what if Mary wants to push it at constant velocity? And this will just be quick because I've already done a lot of the work here. Well, if she wants to keep it at constant velocity, then the forces have to be balanced. Right? Newton's first law, constant velocity means balanced forces. So gravity is balanced with normal, and applied force will have to balance with friction. All right, so then the applied force will just be the force of friction, which is mu times normal so it's just 0.25 times mg. Okay, I'll replace it with mg. So 12, 9.8. And then let's get that there, 27 newtons. Okay, so that's what she'll have to push with if she wants to keep it at constant velocity. And there you go. Okay, we'll just stop at those two examples and we'll let you practice some. Actually, I think I'll do one more example here for you. All right. Police investigators examining the scene of an accident involving two cars measure 72-meter long skid marks of one of the cars, which nearly came to a stop before colliding. The coefficient of kinetic friction between rubber and the pavement is about 0.80. Estimate the initial speed of that car assuming a level road. All right, so skid marks is a common example for a friction problem in physics. So what happens is that the car, the person slams on the brakes, and then that'll cause the car to suddenly try to stop, and it might slide along the surface of the road, leaving skid marks from the tires. So the 72-meter long skid marks will represent the displacement that the car traveled before it was able to come to a stop. All right, so we're asked to find out what the starting velocity of the car was if it traveled 72 meters before it was able to come to a near stop. Okay, it says nearly came to a stop, so I'll say V2 is 0. All right, they tell us the coefficient of kinetic friction, 0.80. All right, so when you look at this, you may think, okay, I'm going to have to use some Unit 1 stuff here. Okay, you got some V1s, V2s, and displacements. So you'd be correct in thinking that. However, normally we need 4 items in our list. Normally we know 3 of them and we can solve for the 4th one. Right now we only know 2 values, so it's not quite enough to solve for the V1 yet. So we've got to do some work first before we can use the Unit 1 equations. And remember, the connection between Unit 1 and Unit 2 is acceleration. Okay, so I want to actually somehow use friction. Okay, somehow use this information about friction to do something with acceleration here. So a free body diagram of the car will look like this. So force of gravity down, normal force up, and they are equal. Now the car is slowing down to a stop, and that's friction slowing it down. And that's all the forces on the car, actually. There's going to be no applied force in this situation. It's just trying to slow down due to friction. Now, if we take this free body diagram and we try to apply Newton's second law to get the acceleration, so here's Newton's second law. Acceleration is net force divided by mass. Now, what is the net force in this case? Well, since normal and gravity cancel out, the net force is actually the force of friction. Okay, the net force is the force of friction. And we know the formula for the force of friction. It's mu times the normal force. So I replace the force of friction with mu times the normal force. But we also know that the normal force is equal in size to the force of gravity. So I replace it with mu times the force of gravity. And finally, we also know the formula for the force of gravity, which is mg. And now I notice that I have an m in the numerator and an m in the denominator, which can cancel out. So my acceleration is actually equal to mu times g. Okay, so that's going to be 0.8 times 9.8. And I get 7.84 meters per second squared to 2 sig figs. Okay, now that I know the acceleration, I can go back to my unit 1 formulas and find the initial velocity. Okay, so I'll add into my list here acceleration. It can be added to my list. Now the direction of this is going to be backwards. So I'm going to put a negative sign with a forward direction because my 72 meter displacement was forwards. Got to have everything in the same direction. I made them all forwards. Okay, so now I search for the formula that relates all those variables. You can look on the formula sheet. But there's the formula that relates all those. The V2 is 0 because it's coming to a stop. So I'm solving for V1. So I can start by subtracting 2AD both sides and then square rooting. Okay, now I can fill in the values. And put it in the calculator. And that gives me 34 meters per second.